So in today's video, we are going to study an important topic based upon the law of conservation of energy as well as the Newton's laws, a combination of both the concepts, which is called motion in a vertical circle. So as the name of the topic suggests, let's understand what the situation is. We have a particle which may be like a small bob of mass m, and it is attached to a string of length r. Okay. And this is suspended, the upper point of the string is suspended at a certain point O, about which this bob of mass m can now rotate in a circle. Now this circle is kept in such a way, like the circle is in the vertical plane. For what this means basically is, you all know there is something that we call as a pendulum, right? A pendulum is a string mass system which oscillates simply about its mean position, isn't it? It oscillates to and fro like this, right? But that's for a certain velocity that the bob will have at the lowest position. By the time it reaches to an extreme, its all velocity is gone, it becomes, it comes at rest, and thereafter it starts moving back. Now, if you keep on increasing the velocity that you provide to this bob at the lowest point, do you understand a point will come where this bob will overshoot this position and will be able to go all the way up to the highest point, and then it will be able to come back by completing the whole vertical circle in the vertical plane, right? So, it is this vertical motion that we are talking about. It is a vertical circle in which our bob is going to move now. So, it is not a normal pendulum which simply oscillates. It is a particle which goes all the way up to the highest point and then completes the vertical circle. Okay. So, the situation is, or what we are supposed to work upon is, we are supposed to find out the minimum speed v naught that must be provided to this particle of mass m here at the lowest point, so that it is just able to complete this vertical circle and is able to reach at the highest point, and thereafter it is able to come back also. So, just for the sake of convenience, if we just consider some point, let us consider the lowest point as A, the highest point of the circle as the point B, then we want this bob to be moving from A to B and then back to A in a full circle by initially just providing a velocity v naught to the bob. After that, no external force, like external agent, won't be coming in and exerting a force on it. It has to move on its own, okay, only under the effect of gravity as well as the force that will come and act on it from the string. Okay. So, let us understand the dynamics of this particular situation. Do you understand, all of you, that the only forces acting on the bob as it moves at the lowest point A, if we take for a mass m, the gravitational force acting on it in the downward direction mg, whereas the force of tension T coming and acting on it from the string, right? These are the only two forces that will act on the bob at any position for that matter, right? Do you see that out of these two forces, mg is a conservative force, right? So, this means that because of the work done by the gravitational force, there will be no loss of energy, the energy will remain conserved. On the other hand, if you look at the work done by tension, just look at the lowest point itself. At the point A, do we understand that the bob will move like this along the horizontal at the lowest point, whereas the tension is acting vertically upward. So, the tension and the displacement that the bob will undergo at the lowest point will be perpendicular to each other, and we can check this at any other point also. Let us consider any other position of the bob. Let us say the bob after some time reaches over here, so that it is making a certain angle with the vertical, let us say, let us call this angle as theta. Do we understand that at this point also that force of tension will be acting along the string, which is now towards the center, the point O, whereas the bob as it moves, it will be moving along the tangential direction. This is the direction of velocity that the bob will have at any point in time, and we see that tension and the velocity direction are again perpendicular to each other. Now, when we say velocity, it is actually the direction of instantaneous displacement. At that moment, what is the direction of displacement? It is given by the direction of velocity, right? So, do we understand that at every point, since the force of tension is perpendicular to the direction of displacement, tension will not do any work on this bob. Work done by tension at any point in time is 0. So the only force that is doing work on the bob is mg, the gravitational force, which is a conservative force, as we have seen in the previous class, right? Previous lecture we discussed about conservative and non-conservative forces and the concept of energy. So since we know that the work done by gravity, here in this case it will not be 0, but then gravitational force as such is a conservative force. So we understand that the conservation of energy principle is applicable here. We can use the law of conservation of energy between any 2 points of motion of this bob, right? So this is one thing that we understand. The second thing is about the forces. See that at the lowest point, let us call the lowest point the point A. So at A, if we have taken the velocity at the lowest point as v naught, the tangential, the velocity along the tangent, can we write the equation for the net force acting on the bob along the vertical, that means along the radial direction? What equation will that be? Do you understand that since this bob is moving in a circle, it will be the equation for the net centripetal force acting on the bob is equal to the mass into the centripetal acceleration. I hope you all understand that when a body moves in a circle, it requires a centripetal force, the one that provides it with a centripetal acceleration. So we write F centripetal, the net centripetal force, which is the net force towards the center of the circular path, is equal to the mass of the body times the centripetal acceleration. If you recall, centripetal acceleration has a value of v squared by r, right? M into v squared by r. This is the usual form that we have. So when we use it at the point A, see carefully that the net force towards the center at the point A is T minus mg, because T is the force towards the center, whereas mg is the force away from the center. So the net force towards the center will be T minus mg. Now this tension here is the tension at the point A, so let us write it as TA rather, because at different points the tension will take different values. So TA minus mg then becomes the net inward force, and that should be equal to the mass into the centripetal acceleration at the point A, which will be v naught squared by capital R, right? So this is the equation that we have for the force equation. Actually the net force is equal to mass into acceleration at the point A, right? So in fact from here we can find out the value of tension at A. We can see here that tension at A is nothing but mg plus m into v naught squared by r, isn't it so? So from here we can find out the value of tension. Now a similar exercise we can do at the point B also, which will be the highest point rather here at the top of the circular motion. Can we say at the point B, look carefully and understand that at the point B, the tension T as well as the force of gravity mg both will be acting downwards now. Tension T is always towards the center in this case, which will be downward now, and mg anyway is downward. So this is the scenario. If the bob at the point B is moving with a velocity vb, let's say, can we say the same equation, net force towards the center is equal to mass into centripetal acceleration? Can we say that that will become T plus mg is equal to m into vb squared by r, right? So from here we see that, and this is the tension at B, so Tb. So from here we can write tension at the point B is equal to m into vb squared by r minus mg, right? So this is another relation that we get. So this is the tension at A and this is the tension at B, the highest point. Understand that at the highest point the tension is mv squared by r minus mg, right? So there is a change of sign in the two equations if we look at that carefully. And now we can look forward to write the equation for force equation at any general point. This point that we have taken over here, which makes an angle theta with the vertical, let's call this point as the point C. Then we can say that at C, if we try to write a similar equation, it will be the net force towards the center. Now this is important here. At the point C, if you see carefully, mg is acting vertically downward like this, right? Tension is acting in the radially inward direction like this. And now if you try to take the net force towards the center O, you will have to consider the component of mg. So here in this direction, the component of mg, because this angle is theta, this angle will also come out to be theta, and the component of mg will be mg cos theta in the radially outward direction. So the net radially inward force then will be T minus mg cos theta, isn't it? So we write it as T minus mg cos theta is equal to m into Vc squared by r, the velocity at the point C. Now we shall be using that into the equation, right? And from here we can write T is equal to Tc, tension at the point C, is equal to mg cos theta plus m into Vc squared by r. Okay, so this is a general tension at any point that subtends an angle theta with the vertical, right? Now there are a few things that we can observe from here. See that as the value of theta increases, the tension decreases, right? And a point comes when theta goes beyond 90 degrees, right? If I take the horizontal level over here, this is the level. If you call this point as the point D, can we say beyond the point D, when the bob goes further up, here at these angles, this angle theta will be an obtuse angle there. And when theta becomes obtuse, cos theta there takes negative values. So when it takes negative values, this whole term will become negative and it will start getting decreasing, no, from this factor. You will have to subtract the mg cos theta factor from mv squared by r to get the tension. Now what is the importance of this fact? Understand that when we try to find out the minimum speed that is required to be given to the particle at A, for which it is just able to complete the vertical circle, we might feel that if the particle has to just complete the vertical circle, what should be the condition? We would think, if we try to think about it, we will feel as if the minimum or the condition for the particle to just complete the circle would be that it is just somehow it is able to reach the highest point, isn't it so? So we might think that if it has to just complete the vertical circle, it should just reach the point B. And if it has to just reach the point B, we might think that the condition for this should be that by the time it reaches the highest point B, its velocity becomes 0 over here at the highest point. So we might try to put that as the condition for finding out the velocity at the lowest point. But if we just look at this condition carefully, this equation that we have got here carefully, at the point B, the tension equation that we have written here, understand that if we put Vb is equal to 0 at the highest point, which we might feel could be true, understand that this term will go to 0 and the corresponding value of tension that we will get at the point B will come out to be negative mg. Negative tension we will obtain at the highest point if the velocity at the highest point is 0. What does that make us understand? That tells us that this is not possible. Do you understand? Tension being negative is not a possibility. Tension can at the most become 0. Tension becoming 0 means the string through which the bob is connected, that becomes a slack system. It is not tight anymore. The string is not tight. So it so happens that by the time the bob reaches over here, the string loses all of its tension, the tension becomes 0, and after that understand that the tension is not there, the bob will fall down like a projectile, because when there is no other force other than mg, other than the gravitational force, a body moves like a projectile, isn't it so? So if the bob undergoes a state of 0 tension in the string, after that it will not be moved in the circle, it will then move like a projectile and it will undergo a parabolic path after that, right? So we understand that if we put Vb is equal to 0 here, tension is coming out to be negative. Negative tension is not a possibility, because before negative tension comes in, the tension would have become 0 and the bob would have fallen down from the circular path. That would have happened even before the point B, somewhere over here. and that means that the bob will never be able to reach to the top, right? So we say that it's not velocity being 0 that is the condition for the bob to be just able to complete the vertical circle. It is the condition that the tension in the string should always remain non-zero till the highest point. So the tension at the point B should become just 0 if we are just trying to find out the minimum condition for the bob to complete the vertical circle. Okay, so these equations, then the force equations that we have written, they give us an idea as to how should we put up a condition for finding the state that we are looking for, the minimum velocity at A for which it just completes the vertical circle. Okay, so now we understand that for the bob to just complete the vertical circle, tension at the point B should become 0. Okay, what does that give us? It gives us, from this equation that we have written for the point B, we get 0 is equal to mvb squared by r minus mg, and that gives us the value of vb at the point B, the velocity at the point B, which if you see carefully comes out to be, from here we can write m into vb squared by r is equal to mg, m cancels out, and from here we get vb is equal to root of gr. So understand that at the highest point the velocity should not be 0, it should at least have a value of root gr. It can have a value greater than that also, but minimum value of velocity required at the highest point for the vertical circle to be completed is root gr. And for this root gr, understand that the tension in the string will become 0 at the highest point. That means the string will just tend to become slack at the point B, but then understand that since at this point it still has a velocity and it moves to the right, as soon as it moves to the right and covers a certain distance, once again tension will come back. Okay, so this is the limiting scenario, then this is the limiting case for the bob or the body to just complete the vertical circle, right? So our exercise is not yet finished. We have just now found the velocity required at the highest point for the bob to just complete the vertical circle, but we were required to find out the velocity given at the lowest point, right? Now to find out the velocity at the lowest point, known the velocity at the highest point, we can directly use the law of conservation of energy between the lowest and the highest points. Okay, how do we do that? We use the conservation of energy principle between the points A and B. How do we use the conservation of energy? We all know when the energy is conserved, that total energy is conserved, the mechanical energy, that means the kinetic plus the potential energy at the point A should be equal to the kinetic plus the potential energy at B. Now let us look at the figure once again. At the point A, the kinetic energy will correspond to a velocity v naught, so it will be half mv naught squared, whereas the point A being the lowest point of this whole figure, we can consider the potential energy at the point A to be 0. This is the reference that we can give here, right? As we have discussed in the previous video, how potential energy is not an absolute quantity, it's always relative. We always find out potential energy with respect to a certain point. So that reference point we have to fix on our own. So here in this case, let's fix that reference point at the point A. So if the potential energy at A is 0, what will be the potential energy at the level B? Do we see here that the point B is at a height of 2r from the level of A, the point A? So can we say the potential energy at the point B will be mg into h, which in this case is 2r, right? So the potential energy at B is mg into 2r, whereas the velocity at the point B we have just now calculated here from the condition of the bob being able to complete the vertical circle. Let us substitute all the values. Kinetic energy at A is half mv naught squared plus the potential energy at A, we have considered it to be 0, is equal to the kinetic energy at B will be half mvb squared plus the potential energy at B, which is at a height of 2r from the point A, it will be mg into 2r. Okay, so this is our law of conservation of energy between the points A and B. We can solve this now. See that m cancels out and we get v naught squared after taking 1 by 2 common everywhere, V naught squared is equal to Vb squared plus 2 times G into 2R. Substitute the value of Vb now. So, we get V naught squared is equal to Vb squared, which will be Gr, plus 2G into 2R, that is 4Gr. So, this gives us 5Gr as V naught squared, and so that V naught is root of 5Gr. A very important expression in the topic motion in vertical circle. The minimum speed required at the lowest point for a body to be just able to complete a vertical circle is root of 5Gr, where R is the radius of the circular path in which the body is supposed to move. Okay. And in this case, we have also understood that the velocity at the highest point will not be 0, it will rather be root of Gr, right. So, like that we can, if we want now, we can also find out the velocity at any other point of this vertical circle also, just by using the law of conservation of energy between one of the points where the velocity is known and any other point if we know its height. So, for example, if we try to find out the velocity of the bob at the point D, this middle point, the one that lies in the same level as the central point O, understand that this point D is at a height of R from the lowest position, right. So, can we use the law of conservation of energy between the points A and D, and can we say to find out the velocity at D, we can write kinetic plus potential energy at A will be equal to kinetic plus potential energy at D. Again, kinetic energy at A is half mv naught squared, and the value of V naught we know now. So, we shall substitute it from here, plus the potential energy at A we have assumed to be 0 is equal to the kinetic energy at D. If we assume the velocity there to be some Vd, we can write it as half mvd squared plus the potential energy of the point D. Because the point D is at a height of R, can we say mg into R will be the potential energy of the point D, right. And from here now, do we see we can easily find out the value of Vd. M goes away, from here we can write Vd squared is equal to V naught squared by 2, the 2 goes away, and into 2 minus 2Gr. When we take 1 by 2 common throughout, this is what we will get, and substituting the value of V naught squared, which is 5Gr minus 2Gr, which is a 3Gr, we see that we get the value of Vd as root of 3Gr, right. So, in a vertical circle which a body undergoes, in case we have given it the minimum required velocity at the lowest point, which comes out to be root of 5Gr, right. We understand that in this case, at the central line over here, the velocity at the point D in this direction will be root of 3Gr, whereas at the highest point at the point B, the velocity in this direction will be root of Gr. I hope now you understand that if we want to find out the velocity at any other point over here, let us say at a point C which subtends an angle theta with the vertical, we can find this out as well. If only we can find out the height of this point C with respect to the point A. How do we get that? If the radius of this circle is R, understand that the length OC will also be R, and in that case this height h that we are looking for can be written as, h can be written as R minus this length, which will be nothing but R cos theta, isn't it so? So, if I call this point, let us say as the point E, the length EA will be equal to the length OA minus OE, right. This is what we have written over here. Once we get the value of h, then we can use the law of conservation of energy between A and C. Conservation of energy between A and C. When we do that, we shall get half mv naught squared, the kinetic energy at A, plus 0, the potential energy at A, is equal to the kinetic energy at C will be half mvc squared, where vc is the speed at the point C, plus mg into h, where now this value of h you can substitute it here and solve this expression. See that the answer for Vc will come out in terms of theta. You can actually take r common here and write it as r into 1 minus cos theta and substitute that and solve from there. So, these are some general ways of solving and finding out the velocity at any general point. See that you can do that very easily now. So, this concept is an important concept. It works in a lot of practical situations also, motion in a vertical circle. Now, we can take up a special case associated with motion in a vertical circle. A special case. What is the special case? When a rod is used in place of a string. So, we have seen that we have already used a string of length r and connected it with the bob, right, of mass m. Now, we do not use a string, we actually use a rod now. Rod of length r and connected with a bob of the same mass m. So, what difference will a rod make here? Rod is a rigid body, right? Rod will be a solid rigid body. It is not like a string. What is the basic difference? The basic difference is that a string can become slack. The tension in a string can go to 0, but the tension in a rod can never go to 0. A rod will never allow this bob, which is trying to move in a vertical circle like this, to fall down from anywhere in between. It will make sure that till the time the bob has a velocity, it continues to move in the circular path only. It does not go anywhere else, right? So, in this case now, do we understand that to find out the condition for the velocity required at the lowest point for which the bob will be able to complete the vertical circle becomes quite simple now. All we need to do is we say that if the lowest point is A and the highest point is B, and if the bob has to just complete the vertical circle, the condition for this will be that the velocity at the highest point should just become 0. Now, the velocity can become 0 because there is no role of tension anymore, right? So, in this case, we say that for the vertical circle to be just completed, the velocity at the point B now should become 0. And as soon as we understand this, we can now directly use the law of conservation of energy between the points B and A to find out the velocity at A to be given to the bob so that it is able to complete this circle. So, then we use conservation of energy principle between the points A and B, and that gives us the kinetic energy at A, half mv naught squared, plus the potential energy at A, which we have considered to be 0, is equal to the kinetic energy at B. Now, this will go to 0 because velocity at B has to become 0, plus what is the potential energy at B? Once again, do we see that the point B is at a height of 2r from the point A. So, mgh, that expression for potential energy gives us mg into 2r as the potential energy at the point B. Solve this, see that m goes away and you get v naught squared is equal to 4gr, or v naught is equal to root of 4gr, which is less than root of 5gr if you recall. So, now in case of a rod, a lesser velocity is required at the lowest point for the bob to just complete the vertical circle. Understand that in this case, at the horizontal level, the velocity will become root of 2gr. How do you get this? If you want, you can use the law of conservation of energy between the points A and this point, you can call it as D. And so the law of conservation of energy is still valid everywhere, right? So, you can find out the velocity at every other point. So, these are the two basic cases of an important topic called motion in a vertical circle. Let us now take up a few examples, a couple of examples let us take to see how we use this concept into practical situations. So, we have this first example which says that there is this inclined track which ends up into a circular track of radius r, like this. We are supposed to find out the height, the minimum height of this inclined track required so that when a bob is released from this height, a bob of mass m or a block of mass m is released from this height, it is able to just complete this vertical circle on its own. Okay, that is the question. Understand here that as the block of mass m slides down over this incline by the way is a smooth one, so no friction here, so no loss of energy anywhere. we are supposed to find out H minimum, right? So as the block slides down, do we understand that from a height of h, as it slides down and reaches the bottommost point over here, it will lose all of its potential energy mgh, and all that energy will be converted into the kinetic energy, because it will have some velocity over here at the lowest point then. And do we understand that after this, as the bob moves along this circular track, it will be the same case as that of a string mass system. The only thing is, in case of a string connected with a mass, as the mass moves, the tension force creates the necessary centripetal force and gives it the force to move in a circle. Whereas in case of a track like this, it is the normal reaction coming from the track acting on the block that will provide the, that will play the same role as that of tension played in the string system, right? Everything else remains the same. There is no difference at all. You only have to replace tension with a normal reaction. Everything is the same, which means that the results are also the same. What is the result? If we want this block to be able to complete this vertical circle, by the time it reaches the topmost point, its velocity should be root of gr, which also means that the velocity at the lowest point should be root of 5 gr, right? So all you need to do now is, you choose any of these 2 points, the point A or the point B, and use the law of conservation of energy between the starting point, call it the point O, and any of these points A or B. So we can directly maybe use the conservation of energy between O and point A, saying that the kinetic energy at O, which is 0, plus the potential energy at O, which is mgh, should be equal to, just equal to, the kinetic energy at A, which we want to be half m into root of 5 gr whole squared, right? This is the velocity that we want at the lowest point for the block to be able to complete the circular path. Plus, what is the potential energy at the lowest point? Do you understand? Since we have taken the potential energy at a height h is 0, that means we are assuming that the potential energy at the ground is 0. So the potential energy at the point A will be 0, right? Now can we solve this equation? M goes away and we get 2gh is equal to 5 gr, and from here we get h is equal to 5 by 2 r. That will be our answer. Simple. Using the result that we have obtained in the previous exercise, use it here directly in the conservation of energy principle and get your answer. Let's look at one more example here. So the question says that there is a figure that shows a smooth track. The track is like this, and it ends up in a circle of radius r once again. Now what we have is a block of mass m is connected through a spring like this, and it so happens that this block is pressed against the spring, so that it compresses the spring, and after that it is released. Now as the block is released, it gains a kinetic energy and it reaches this point A, the lowest point of the circular track. The question is, find the initial compression of the spring x, the compression created in the spring, so that the block presses the track with a force of mg when it reaches the point P. Where is the point P? The point P lies at the horizontal level point which is leveled with the center of the circular track. So point P lies at the same horizontal level as that of the center of the circular track, but on the track, right? So it is at the point P that the bob presses the track. Presses the track means it creates a force on the track which is equal to mg. We are supposed to find out the compression x required in the string for this to happen. Let us understand the question carefully. Do we see that when we compress the spring using the block, and then when we release it, the spring will create an outward force on the block, due to which by the time the spring opens up back, the block will gain a kinetic energy, which will be nothing but the potential energy that was initially stored in the spring, right? So understand that if x was the compression in the spring, the energy, spring potential energy stored in the spring was half kx squared, and when you release the block and the spring opens up, all this spring potential energy will be converted into the kinetic energy of the block, half mv naught squared, and it is with this kinetic energy that the block reaches here to the point A. So, as it moves from the point A and it reaches the point P, do we understand it loses some of its velocity because it is gaining a height? It will lose a velocity, which we can find out easily. We can actually find out the speed of the bob at the point P by using the law of conservation of energy between the points A and P, right? Now, due to the velocity v that the bob has at the point P, do you understand that if I draw this figure separately over here, at the point P, when the bob is like this and moving up, do we understand that the bob will require a centripetal force which needs to act on it to provide it the necessary centripetal force? What is the nature of this centripetal force here? Do we understand the centripetal force is coming in the form of the normal reaction coming from the wall of the track? It is this normal reaction which is acting towards the circular center of the circle that provides the centripetal acceleration. So, we can write N is equal to mv squared by r for the block. Now, it is this force that due to which the bob moves in the circular path. This force is coming from the track and acting on the block. Do we understand that by the Newton's third law, the block will exert the same force back on the track? So, if the track exerts a force N to the block will exert the same force N to the track in the opposite direction. According to the question now, this force that the block exerts on the track N is nothing but mg. That's the condition, right? So, if we put N is equal to mg here, can we find out the value of velocity? Right? Can we say that mg, if it is equal to m into v squared by r, from here we get v is equal to root of gr. So, we get the velocity of the block at the point P, and can we use that by conserving the energy between the point A and P, right? So, can we say conservation of energy between the points A and P give us the kinetic energy at A, which is half mv naught squared, plus the potential energy at A, which we can consider to be 0 because the point A is on the ground, is equal to the kinetic energy at P will be half m into v squared, where we have got as root of gr. So, it will be v squared means gr itself, plus the potential energy at P. Now, since P lies with the level at the level with the point O, can we say its height from the ground will be nothing but the radius of the circular track r? So, can we say that its potential energy will be mgr, right? So, from here now, connecting this equation and this equation together, we can solve for x in terms of the other quantities. So, see that half mv naught squared that we are using here on the left hand side, its value is actually half kx squared. So, instead of this half mv naught squared, I can put half kx squared is equal to, on the right hand side we have half mgr plus mgr, that will be 3 by 2 mgr, and now we can solve this. So, 2 goes away and we get x squared is equal to 3 mgr by k, and so x will be equal to square root of 3 mgr by k. So, this gives us the compression to be created in the spring so that the block can press the circular track with a certain force at a certain point.